Good evening, Sunderland. The end of everything, as you can hopefully see from the subtitle. I'm talking about ultimately the fate of the Earth, the fate of the Sun, the fate of the galaxy, and eventually the fate of the universe. So if you will forgive me paraphrasing our friend Buzz, we're going to eternity and beyond. So I'll be giving a little bit of a prologue and then talking about the future of the Earth and the Sun and the solar system, and then looking to the far, far future of what's happening to stars and galaxies. And then I'll be looking at the far, 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 far future and the ultimate fate of the universe. And so as not to leave you too depressed, I will finish with a little bit of a more upbeat epilogue. So a year or so ago, I told you about the beginning of everything, how the universe started as a very small, hot, dense state. Everything that we now see in the observable universe used to be only a few centimetres apart. And ever since then, it's been expanding and cooling. And this is looking at the story from the other side, from where we are now into the future. And to try and keep track of where we are, I've got this timeline across the top. Each box represents 10 times further into the future than the previous box. So we'll be looking at, for instance, 1,000 years into the future, or 1,000,000 years, or 1,000,000,000 years, or perhaps 1,000,000,000,000 years into the future. And so that red rectangle will allow us to keep track of how far into the future we are talking. And I'd like to acknowledge the work of Adams and Laughlin, who published a paper about 25 years ago, on which they published the timescales on which various astrophysical phenomena are likely to occur. And I've used that publication to try and get my slides in the right chronological order. So we're not going to start in the next few years. Let's assume that we get climate change under control. Let's assume we don't have a nuclear war. In 10,000 years, we know things are going to change. Because of the way the Earth spins, because of this precession that you can see on the left-hand side there, the pole star is going to change on a 26,000 year cycle. So the direction in which the Earth's axis points traces out this large circle in the sky. At the moment, the pole is pointing roughly towards Polaris. It's less than a degree away from Polaris. But on a timescale of 10 to the 4 years on the future, the Earth's axis will be pointing in the opposite direction, closer to the bright star Vega. Now, apart from the fact that this is going to make it very easy for Boy Scouts to point out which way is north, that life becomes a lot easier rather than trying to find Polaris, it does have a consequence for us. If you think about the direction of the Earth's axis pointing towards Polaris or pointing towards Vega, at the moment we're nearer to the Sun, perihelion, during northern winter, and that tends to mitigate the seasons to somewhat. But when we point the other way, such that we are nearer to the Sun during northern summer, when we're pointing towards Vega rather than pointing towards Polaris, that means the seasons are going to be just a little more exaggerated. And these variations in the Earth's climate that are due to either the way the Earth is spinning or in its orbit around the Sun, these are collectively known as Milankovitch cycles. On a scale of 10 to the 5 years into the future, 100,000 years into the future, the space probes, Voyagers, are going to pass by nearby stars. They were launched in the 1970s along with the Pioneer spacecraft, and Voyagers went past Jupiter, Saturn, and Uranus and Neptune in the case of Voyager 2. And they are now leaving the solar system. At the top there, Voyager 1 is heading off towards the star system Gliese 445 and will be passing through that solar system on this sort of timescale. At the bottom of the screen, Voyager 2 is heading off in the direction of Ross 248. Pioneers were launched a little earlier. Pioneer 10 on the right-hand side is heading off in the direction of Aldebaran, and Pioneer 11 on the left-hand side is heading off towards the centre of the galaxy. Still, on a timescale of 10 to the 5 years into the future, we know that we're likely to be in another ice age. Historical records tell us that ice ages come and go on a timescale of order 100,000 years. And the Earth entered an interglacial phase, in other words, a warm phase between ice ages, relatively recently, and so we can predict that an ice age is on its way on this sort of timescale. This is another manifestation of a Milankovitch cycle due to changes in the Earth's orbit. Now, the moon is affecting the Earth's rotation. This is in a separate short talk that I give about how tidal effects of the moon are slowing down the Earth. So at the moment, the Earth's rotation is about one rotation in 24 hours. But when we go 100,000 years into the future, instead of adding leap seconds occasionally, which we need to do to keep the Earth's rotation synchronized with our clocks, the Earth's rotation would have slowed down to the point where we would need to add a leap second every day rather than just once every few years. It's been quite a few years since we've introduced a leap second into our clocks. Still on a timescale of order 10 to the 5 years, we think a number of possible stars could go supernova. For instance, Eta Carinae in the southern hemisphere. This is a picture of the nebula that's been produced by the outer layers of this star being sloughed off for perhaps thousands, maybe tens of thousands of years in the past. This star is getting very unstable. We know it's very massive. We know it's a candidate to be supernova. We don't know when that's going to happen, but it's likely to happen on this sort of timescale. It could be beaten by Betelgeuse in the northern hemisphere. Here's an astrophoto that's been enhanced by the photographer to show what Betelgeuse might look like when it goes supernova. Not only will it be a very bright star in the sky, it probably will be visible during the day as well. But there are other things that could be a problem for us, not necessarily nearby supernova. There are certain Wolf-Rayet stars that we think are associated with gamma-ray bursts. This particular one, Wolf-Rayet 104, is 7,000 light years away, some 10 times further away than Betelgeuse. And yet that's still close enough to be a possible problem, because when it dies, it might produce a radiation burst even more powerful than a supernova. That's because these systems are very rapidly rotating and have these jets, as indicated by this artist's impression. If the jet happens to be pointing at Earth when it dies, it could produce a gamma-ray burst that would be a significant threat to Earth. We don't think the jet is pointing in our direction, but we're not absolutely sure. On a timescale of 1 million years into the future, because all stars like our Sun are orbiting the Milky Way, they're all in independent orbits, so even the stars close to us are on slightly different orbits, and every once in a while one of our neighbour stars comes close to us. And by monitoring the positions and velocities of stars, we've come to the conclusion that Gliese 710 is a nearby star that will come close enough to actually enter our Oort cloud, our cloud of icy particles that are quite some considerable distance away from our Sun. When Gliese 710 comes that close, it will disrupt the Oort cloud, and it will almost certainly produce loads of asteroids and comets coming in our direction, perhaps naked eye comets once a month for 1 million years. It's difficult to predict exactly how many it will produce, but it's likely to be very disruptive when it gets that close to our solar system. And it's interesting to note that for a short while, our solar system will actually have 2 suns, just like other planets we know about. Still on a timescale of 10 to the 6 years, here's a picture of meteor crater. Does that mean we can expect an impact like this every 1 million years? No, we're probably going to get them more often than that. This particular picture reminds us, one, wasn't it really lucky that this impact just missed the visitor centre? But also it reminds us that any impact on Earth is likely, due to weathering, to be lost. So craters that are relatively young, like this one, only tens of thousands of years old, will be preserved. But any crater that's more than, say, 1 million years old is likely to be lost. We're unlikely to see any traces of it because of weathering, because of the effects of wind and rain and ice, etc. You might say, well, yes, that's going to happen on Earth, but it won't happen on the Moon. Anything that lands and produces a crater on the Moon, the crater lasts forever. Well, not strictly true, because the Moon is constantly being pulverized with micrometeorites. So even the Apollo footprints, for instance, are eventually going to fade away to nothing because of this micrometeorite impact. Not quite the same as weathering, but ultimately it will produce the same results. Eventually, all evidence of the Apollo moon landings will be erased. On a timescale of 10 to the 7 years now, we're talking 10 million years into the future. The Pioneer spacecraft that I mentioned that were leaving the solar system have got plaques on them so that when they pass through solar systems, remember they could pass through a solar system on a timescale of tens of thousands of years. So after 10 million years, they will have probably passed through hundreds, if not thousands, of solar systems. And this plaque will allow anybody that sees the spacecraft going by or pick it up, they'll know where it came from, because the plaque has a pulsar map, which basically tells you where the sun is in the galaxy, and a little icon at the bottom says we came from the third rock from the sun. So if anybody picks it up, in principle, they could decode this plaque and figure out where the Pioneer spacecraft came from. But only up to a timescale of order 10 to the 7 years. Pioneer will be flying through other solar systems on timescales greater than that, but this plaque is going to get pitted and eroded on this sort of timescale. Simply because the interstellar medium is not empty, it's full of tiny dust grains, so as Pioneer flies through it after millions of years, it's going to get pitted and eroded and ultimately unreadable. So although Pioneer might continue its journey far beyond 10 to the 7 years, anybody that picks it up won't know where it came from on timescales greater than this. What about Saturn's rings? We're now talking about 10 to the 8 years into the future. What do we think is going to happen to Saturn's rings? Well, it's probably best to answer the question first, where did they come from? It is thought that maybe a moon such as a moon like Mimas might have disintegrated and made Saturn's rings. When you look at this image of Mimas, you might think to yourself,
that's no moon, it's a space station.
Because it does indeed bear a certain resemblance to the Death Star. But if it was a case that pulverizing a moon, perhaps by colliding with another moon or a comet might have hit a moon, what would that have done in terms of making Saturn's rings? Is it possible that one moon can make a ring system? Well, this simulation has been done, taking a moon about the size of Mimas, pulverizing it, and then ask what happens next. You might think that the cloud of pulverized dust would simply go around the globe of Saturn in much the same way that the original moon did. But actually, these simulations show that because all of the tiny particles are interacting with each other, you can see that it's only a matter of days or weeks before a pulverized moon actually makes a ring system. So actually making a ring system is really fast. And we think over millions of years since that happened, all of the individual particles have slowly been migrating inwards because they're all interacting with each other, all of these trillions of tiny particles in the ring system. And that's where we see Saturn's rings at the moment, but this process is continuing. In other words, all of the individual particles in the ring system are slowly spiraling inwards and eventually will simply rain down on the surface of Saturn. So on a timescale of 10 to the 8 years into the future, Saturn's rings will probably be no more. So for those of you who like and enjoy the sight of Saturn through a telescope, get in now because they won't be there forever. Still on a timescale of 10 to the 8 years into the future, we have to remind ourselves that the solar system is not a totally predictable system. We might build ourselves an orrery and say, yeah, everything seems to be going round like clockwork, regardless of whether it's all the planets or whether it's the moon going around the Earth and the Earth going around the sun, as in this Tellurian. But on a timescale of 10 to the 8 years into the future, the solar system is essentially chaotic. In much the same way that we can tell what the weather is going to be tomorrow, but we can't tell what the weather is going to be in 1 month's time. It's the same for the solar system. We know where the planets are going to be for thousands upon thousands of years into the future, and we know where they have been thousands of years in the past. But we can't extend that indefinitely. We can't figure out where the solar system planets are going to be in 100 million years' time. We don't even know how many planets there will be. Maybe Jupiter or some of the other planets have decided to eject some of the smaller bodies from the solar system. It can happen. It has happened in the past. It might happen in the future. Still on a timescale of 10 to the 8 years into the future. We are roughly there in this map of the spiral arms of the Milky Way. At the moment, we're sitting between spiral arms. We're on the so-called Orion spur, in between two spiral arms. And it takes us, of order, 10 to the 8 years to go around the Milky Way. It's been predicted, based on the movement of stars that we can see at the moment, that as the Milky Way rotates, as the sun goes around the Milky Way, we are going to move from a relatively low density region in between spiral arms. We're going to move into one of these spiral arms, a higher density region. In other words, we are going to have a lot more stellar neighbours on a timescale of order 10 to the 8 years into the future. So what? Who cares if we've got more stellar neighbours? Well, there are two consequences of having stellar neighbours. One of them we've already seen. For instance, we've seen Gliese 710 is going to get close. It'll disrupt the Oort cloud. It'll send lots of icy bodies our way, and we're more likely to have an impact on Earth. So, looking back at the historical record, we see that extinction level events have occurred many times on a timescale of the last billion years. So it looks like on timescales of order 10 to the 8 years, extinction level events become more likely. The last one, of course, was the so-called KT boundary, the boundary between the Cretaceous and the Tertiary eras. That's the impact that killed the dinosaurs. So it is likely, it's again impossible to be precise, but it's likely that we're going to get an extinction level event on this sort of timescale. This, of course, is an artist's impression of what a large rock possibly being disturbed by the Oort cloud might look like as it comes hurtling towards Earth. Now, if you look on the left-hand side, you can see that this is really bad news for Italy, because it looks like it's going to hit them. But if it's a large enough piece of rock, it'll be bad news for the entire Earth. Species will be exterminated if the rock is large enough. The only real question is not if it will happen, but when it will happen, and when it does, will one of the species that is exterminated include us? And of course, we've got a little bit of time to figure out how to avoid such a disaster. The second consequence of having a lot of neighbours is that one of them might go supernova. At the moment, we haven't got any really massive stars close to us. We need a massive star to go supernova because smaller mass stars don't end their lives in a supernova. At the moment, the closest supernova candidate is many hundreds of light years away. But what if we had a lot more neighbours? Well, a supernova within 100 light years of us would be a danger to Earth in terms of the amount of radiation that it would produce. This artist's impression showing a planet getting sliced in half, well, that's a little bit fanciful perhaps, but we do know that a supernova within 20 light years of us might conceivably end all life on Earth. So it is something that we should at some point worry about. And if you think it's rather fanciful, bear in mind it has happened in the past. Supernova within 100 light years of Earth have gone off. Supernova can, if they're close enough, can leave a deposit of a particular isotope of iron called iron 60, and it can leave that deposit in the Earth's sediments. Now, iron 60 is an isotope that decays into something else. The iron decays into cobalt and then into nickel after a few million years. In other words, if we see any in the Earth's sediment, it can't have been there for billions of years. It can't have been there since the Earth was made, because it would have changed into something else by now. So if we see iron 60 in the Earth's sediment, that means it must have been put there relatively recently. Recently meaning certainly less than a billion years ago. So the fact that we do see iron 60 tells us that we have had supernova go off relatively close to us in the past. If it's happened in the past, it can happen in the future. I said earlier that the moon continually raises tides on the Earth and slows the rotation of the Earth. That has been continuing for the last 100 million years, now that we're looking 100 million years into the future. So the moon is actually robbing the Earth of some of its angular momentum. So the spin of the Earth is slowing and it's increasing the size of the moon's orbit, increasing its angular momentum. The Earth has now slowed down, so instead of rotating once in 24 hours, it now rotates once in 25 hours. It's now crazy to think about adding leap seconds into the day to try and keep our clocks synchronized with the rotation of the Earth. Long ago, we would have to abandon the idea of a 24-hour day. Maybe this is a good time to decimalize the clocks. The distance from the Earth to the moon will increase for all of this time as the Earth is slowing its spin, and eventually it'll be the case that the moon is so far away from the Earth it'll no longer be large enough to cover the sun and produce a total eclipse of the sun. So again, for those of you who like to watch a total eclipse of the sun, get in now, because in 1 billion years or so, the moon will be so far away from the Earth, its disk in the sky will no longer be large enough to cover the disk of the sun. And so, although partial eclipses and annular eclipses will still occur, there will be no more total eclipses to be seen from the surface of the Earth. Perhaps a more serious consequence of the moon moving away from the Earth because of the tidal to and fro tug of war between the moon and the Earth. Now that the Earth and the moon are further apart, the moon will no longer be able to stabilize the tilt of the Earth. The tilt of the Earth's axis, called the obliquity, which is approximately 22 or so degrees. That cartoon on the left gives you an idea of the variation of the tilt. It's only ever varied by about a degree either side of its current value. But if the moon ends up going a lot further away from the Earth, perhaps a 25% increase in the Earth-Moon distance might be enough to be resulting in the Earth no longer being stabilized by the moon, in which case the Earth's tilt could radically change. Rather than being fixed at 23 degrees and giving us our familiar seasons, it might go to 0 or it might go to 90 degrees. We could end up with a wildly varying climate if the Earth's axis is no longer stabilized. On a timescale of 10 to the 9 years into the future, the gold disk that's been taken by Voyager out to the stars, well, it's going to be difficult to read that. Remember, the Pioneer plaque ended up getting pitted and eroded after 10 million years or so. The Voyager gold disk is going to last longer because it's protected, the disk on the right is protected by the lid on the left, a protective cover. Now, although that means the cover is going to get pitted, which will protect the record inside with songs and welcome messages from Earth, well, unfortunately, it's the cover on the left-hand side that contains the instructions for how to read the disk. So even if some extraterrestrial intelligence does pick up Voyager and then realizes there's a disk attached, it won't be able to read the instructions if it waits more than 1 billion years or so from its original launch. Maybe that doesn't matter. Maybe anybody that picks it up after 1 billion years will be intelligent enough to figure out how to read the disk, even if the instructions have got essentially unreadable. Still on a timescale of 10 to the 9 years into the future. The Sun is a main sequence star and it will be changing after many billions of years. But even before it gets to its red giant phase, the Sun's luminosity will slowly increase, perhaps by as much as 10% every billion years. So even before it reaches red giant, it is going to get more luminous. And that means the Earth is going to get warmer. Perhaps on a timescale of a few billion years, the Earth will be driven to a temperature of some 80 Celsius. The oceans will boil. We'll have to find somewhere else to go. Going underground isn't going to help. We're going to have to go somewhere else and come back to the Earth when it's cooled off a little bit. But the sun is going to swell up and become a red giant, which means the surface of the sun is going to swell until it ends up being comparable to the orbit of the Earth. So if the surface of the sun gets close to the Earth, could that possibly be a problem for us? Well, it's not absolutely clear whether the sun is going to engulf the Earth or not. And it's a difficult calculation to be precise with, which is why people differ as to what the ultimate result will be. And that's because as the sun expands, almost certainly, yes, it will expand until the surface of the sun is comparable in terms of radius to the orbit of the Earth. But the solar wind will result in the sun losing mass. And if the sun loses mass, there's less gravity pulling on the Earth, which means the orbit of the Earth is going to expand. So this little cartoon on the left-hand side shows that as the sun gets bigger, yes, it engulfs the original orbit of the Earth, but the Earth isn't there anymore. The Earth is now in a new orbit, perhaps out where Mars is now, simply because the sun, despite swelling up, is now less massive than it used to be. So we don't know whether the Earth will be engulfed or not. The jury is out on that one. Let's assume the Earth survives. Let's be optimists about this. Once the sun has gone through its red giant phase, it'll slough off its outer layers and produce a rather beautiful planetary nebula, and the core of the sun that's left will become a white dwarf star. Now, if the Earth survives that, it has another problem to contend with. And that is that on this timescale, quite a few billion years into the future, the Earth is going to lose its magnetic field. The Earth has a magnetic field because it has a molten core that's rotating, and a molten metal rotating core produces a magnetic field. The Earth's core is molten not because of heat from the sun, but because of its internal energy source, which is radioactive decay of elements that have been made way back in the original origins of the solar system. So ultimately they will not be enough, these radioactive decay of elements in the Earth's core. Ultimately, eventually the radioactive decay dies away and it will not be enough energy to keep the core molten, so the core will freeze. We no longer have a dynamo, we no longer have a magnetic field. And if we no longer have a magnetic field, we can no longer get the protection that we've been getting up till now from particles from the sun and particles from cosmic rays. Now, perhaps once the sun has gone through its red giant phase and is now a white dwarf, radiation from the sun is not so important. But we do still need some protection from cosmic rays. So this is bad news if we lose our magnetic field. And they say bad news comes in threes. So if we survive the sun going through red giant phase, if we survive the loss of a magnetic field, we then have to contend with the fact that the Andromeda galaxy is going to come and collide with the Milky Way galaxy on a timescale of a few billion years. So the Andromeda galaxy is going to end up as a huge object in our sky. For those that like astrophotography, you will no longer need a telephoto lens to take a nice picture of the Andromeda galaxy. If you wait long enough, you'll need a wide-angle lens to get it all in because it will be coming so close. At some point, the two galaxies will pass through each other on a timescale of 4 to 5 billion years into the future. That's not as cataclysmic as it sounds, because stars will probably not hit each other because they are so far apart from each other, but the gas and the dust will interact to the point where there'll be a riot of new star formation as the two galaxies pass through each other. The sun might conceivably be pulled out of the Milky Way. If it does, well, the planets will go with it. It won't actually make any difference to any local evolution. The two galaxies will pass through each other and then by gravitational attraction will eventually merge with each other after 5 or 6 billion years. When that happens, both galaxies will have lost their spiral arms and will end up with one probably large elliptical galaxy with two nuclei, because the supermassive black holes at the centre of Andromeda and the centre of the Milky Way will orbit each other for quite a while, and then they eventually will merge together. So, although it's a spectacular event, it won't actually necessarily dictate the fate of the Earth. On a timescale of 10 to the 11 years, 100 billion years into the future, the dance between the Earth and the Moon finally comes to an end. Up to this point, the Moon has been slowing the rotation of the Earth, but at this point, the rotation period of the Earth, 1 day, is the same as the rotation or orbital period of the Moon, 1 month. So in other words, as well as the Moon always facing one face towards the Earth, the same will be true in the opposite direction. The Earth will be tidally locked to the Moon so that one side of the Earth always faces the Moon. In other words, from certain continents on the Earth, the Moon will be fixed in the sky, and from certain continents on the Earth, the Moon will never rise. This is just what's been happening on the Moon for billions of years, but ultimately it'll also happen to the Earth, so that the Earth and the Moon as a pair will always be facing each other. The two faces will always be looking at each other, just like Pluto and Charon do at the moment. And although this looks like a Photoshop on the right hand side, this is a genuine picture of the Earth and the full Earth and the full Moon. But of course this is the far side of the Moon, not the near side of the Moon, which is why it looks a little bit odd. On a timescale of 10 to the 12 years into the future, 1 trillion years into the future, if we look at what's going on in the vicinity of the Milky Way is surrounded by lots of very small satellite galaxies, little dwarf galaxies. And ultimately, those are going to be hoovered up. Those are going to be absorbed by the Milky Way. And we've already just seen that on this timescale, M31, the Andromeda galaxy, is going to collide with the Milky Way, and eventually M33, the Triangulum galaxy, will as well. So essentially all of the galaxies, the big ones and all of the small ones in the entire so-called local group of galaxies, they're all going to end up merging into one large galaxy. It's not going to be a spiral. That icon is just there for show. It's probably going to end up as one large elliptical galaxy. What's going to happen to galaxies beyond our own local group? Well, it is now possible to see galaxies at huge distances at the moment. So for instance, as of time 0, as of now, it is possible to look at galaxies. For instance, during the COVID lockdown, I actually imaged a quasar, which is the center of a very active galaxy. I imaged a quasar that is receding from us at a speed of twice the speed of light. It is so far from us because of the expansion of the universe, it is being taken away from us at a recession velocity greater than twice the speed of light. Even so, it is possible to image these galaxies. I imaged that quasar actually without using a telescope, just using my camera. And if we look on the right hand side, there's a Hubble deep field. It's the ultra deep field, where a lot of those galaxies are so remote because of the expansion of the universe, the recession velocity of some of those galaxies is greater than the speed of light. But on this timescale, 10 to the 12 years into the future, how is that going to change? Well, for all of these 10 to the 12 years, the universe has been continuing to expand, and so all of these galaxies are being taken further and further and further away. And on a timescale of 10 to the 12 years into the future, all remote galaxies are going to be so remote that we will not be able to image them. So if a technological civilization in 10 to the 12 years' time builds themselves a Hubble Space Telescope and looks out into the universe, what will they see? They will see nothing other than the stars that are in their own galaxy, such as these two stars which are in the Milky Way as imaged by the Hubble Space Telescope. So it doesn't matter how good their telescope is, if they want to know what universe they live in 10 to the 12 years' time, if you want to know what the universe looks like, you will come to the conclusion that the universe is empty apart from your own host galaxy. Quite a sobering thought that we live in a time where we know that we live in the Milky Way and we know that there are at least 1 trillion other galaxies. But in due course, no civilization would be able to come to that conclusion. I said last year in the beginning of everything that it took 3 minutes to make all of the hydrogen in the universe. After trillions of years, it's nearly all gone. And if the hydrogen has gone, you can't make new stars. Well, just as an aside, some people say, well, maybe you can. Maybe you can make new stars, but not using hydrogen. Maybe you can make stars from heavier gases. And some theorists have said if you could do that, it might be possible to make a star with nuclear reactions at the core, but low surface temperatures, 10 times lower than the surface temperature of a red giant. Not a few thousand degrees, but a few hundred degrees. It might be possible to make a star whose surface temperature is so low, ice might form. A so-called frozen star. Well, yeah, okay, for those of you who are thinking about Disney and Disney's version of Frozen, that's not the sort of star I'm talking about. So if that's the sort of picture you've got in your head, well, let it go, because what I'm talking about is nuclear reactions in a star and ice in the atmosphere. Some people believe that's possible. Plenty of scientists say, no, you absolutely can only make stars in the first place using the lightest of elements, hydrogen. To make sense of what happens when the hydrogen runs out, we have to have a little bit of an aside and ask ourselves, what does the long-term evolution of the universe look like? This is a graph of the expansion of the universe, or rather the size of the universe on the vertical scale as a function of time on the horizontal scale. That's where we are now with the universe of its current size. And you can see that when did the Big Bang happen? How old is the universe? Well, that depends on which of those coloured lines that we are following. And the different coloured lines correspond to how much matter and how much energy there is in the universe. So, for instance, if the universe was full of a huge amount of matter, then we would be following the orange line, in which case the universe would expand for a while, but then would start to contract and we'd end up in a big crunch, a so-called closed universe. When I was young, we used to think that we were on the green line, but now it looks like, well, the best guess is that we're on the red line. If you look at how much matter and energy there is in the universe, it looks like we're on the red line. And notice the gradient there. The universe is not only getting larger, but the gradient of that red line is getting larger and larger. The universe is continuing to expand, it would appear, forever. And the rate of expansion is continuing to get faster and faster. This was a bit of a surprise until 20 years ago when observations were made. But if that's the case, then let's assume that that is correct and that we're not going to have a big crunch. Let's assume the universe goes on expanding forever. To make sense of what's coming, we're going to have to change gear somewhat. So the numbers at the top of the screen have now changed. Each small box at the top now represents 1,000,000 times further into the future than the previous, rather than just 10 times into the future. So we're talking about 10 to the power large numbers, 10 to the 30, 10 to the 48. I don't know if that's a zillion or a gazillion, whether or not we have any descriptors of these large numbers. So where did we leave things before we said the universe is continuing to expand? We said it took 3 minutes to make all of the hydrogen in the universe, but on this timescale, many, many trillions of years later, the hydrogen is running out. Now, stars might last an awful long time. Stars less massive than ours could have lifetimes of many, many trillions of years, but they don't last forever. So what does that mean if there's no more hydrogen? There will come a time when there are no more stars shining. The age of starlight will come to an end. The stars themselves will continue to orbit in their galaxies, zombies drifting around white dwarfs, neutron stars, black holes. It might seem a bit odd to talk about white dwarfs not shining, but white dwarfs have no nuclear reactions to keep them hot. So basically they are only white because they start hot, but then they will cool down. Given long enough, they will simply cool down and become black dwarfs, and there will be no stars shining. Some stars will be ejected from their host galaxies, and some will be eaten by the supermassive black holes at their cores. Magnetic fields have been mapped out in other galaxies. For instance, in this galaxy, the magnetic fields have been mapped out by SOFIA, the Stratospheric Observatory for Infrared Astronomy, an infrared telescope in the back end of a 747 jet. The magnetic fields have been mapped out, and we think that matter simply flows along those field lines and gets effectively funneled into the supermassive black hole at the core of what we believe is every galaxy. What happens to all of the atoms that are in the universe? Well, the nucleus of every atom contains protons and neutrons in the case of heavy elements beyond hydrogen. Protons are particles that are part of essentially every atomic nucleus. And we don't know what's going to happen to protons. It is possible that protons last forever, but it's also possible that they decay or change into something else. If protons do decay, then atoms are going to fall apart. We don't know the timescale on which this is going to happen. We don't know even if it is going to happen. If it does happen, it doesn't happen on shorter timescales than where the box is now, 10 to the 36 years into the future. But it might happen on longer timescales. Let's assume for the moment that protons last forever. If protons don't decay, that doesn't mean atoms are going to last forever, because the only atoms that exist are in black dwarfs. There are none in neutron stars, there are none in black holes, and eventually even black dwarf stars will evaporate. It's a quantum process I'm not going to describe in any detail. So ultimately there will be no atoms in the universe. There will be black holes at the center of galaxies, and as galaxies merge with each other, the black holes eventually will merge, much like the black hole at the center of the Milky Way will merge with the black hole at the center of Andromeda. Supermassive black holes will grow from sizes that might be millions of solar masses, like ours at the center of the Milky Way. They will grow to billions or trillions of solar masses as galaxies merge together. But even black holes are not eternal. They do not last forever. Black holes, as we understand them, evaporate. Admittedly, you have to wait for a really long time, so we can't watch this happen. So this at the moment is conjecture, but most scientists believe this is what actually happens. So why do they evaporate? Well, quantum mechanics allows particles and antiparticles, in other words matter and antimatter, to be created by borrowing energy from essentially nothing and making particles and antiparticles as long as they annihilate and pay back the borrowed energy on very short timescales. In other words, you can borrow energy, make particles and antiparticles which then annihilate and pay back the loan again. So what? Just because quantum mechanics says that can happen, how is that relevant to the lifetime of a black hole? Well, Stephen Hawking and others said, well, what would happen if you have a particle-antiparticle being created just outside the event horizon of a black hole, represented here by the black line? You borrow energy, you make a particle and antiparticle. What happens if one of them falls into the black hole and the other one doesn't? Now they can't annihilate. It looks like something has been emitted from the black hole. This is what we now call Hawking radiation. Still conjecture, but many people believe this is the way it actually is. Black holes appear to radiate particles. Well, ultimately those particles turn into radiation, and ultimately black holes radiate energy and evaporate. Small black holes evaporate faster than large black holes. So if you were to watch an individual black hole radiating, the radiation levels would increase as it gets smaller and smaller and smaller until it finally dies in a flash of radiation. And even the big ones, even the supermassive ones, which radiate much more slowly, even the supermassive black holes lurking at the centres of galaxies that might be trillions of solar masses, even they will evaporate eventually, though it will take many trillions of times longer than for stellar mass or other large black holes. So notice the red rectangle has now reached the right-hand side yet again. Have we reached the end of time? Well, near enough. If we think of 10 to the power 100, which is a googol, no, not that googol. That googol is just a misspelling of the actual googol. 10 to the power 100 is a googol. After a googol years, it has been calculated the last black hole in the universe should have evaporated. So there is no matter left at all. The universe is just full of radiation and nothing else. And hence, nothing happens from this point onwards. So you could argue that time becomes essentially meaningless. If we just have a think about what 10 to the power 100 actually looks like, I've resisted the urge to put lots of zeros on the screen up till now, but I think for 10 to the power 100 we have to do that. That's what one googol looks like. 10,000 million, you can do it yourself. It's a ridiculously large number. But just because we cannot imagine that number doesn't mean we can't do the calculations and work out the quantum theory tells us this should happen on this timescale. Again, I ask the question, is this the end of time? Well, eternity is a very long time, especially towards the end, as Woody Allen said. But I do like the quote from the satirical magazine XKCD. They had a particular way of looking about how human lifespans fit into this ridiculously long timescale. They say a human is a system for converting dust billions of years ago into dust billions of years from now via a roundabout process which involves checking email a lot. That's one way of looking at the human condition. But so as not to leave you all thoroughly depressed in that everything is going to come to an end, let me finish with a slightly more upbeat epilogue. We live in a golden age. The sun is middle-aged and well-behaved. The moon is at just the right distance to stabilise the Earth's axis and hence to stabilise the seasons, to give us a nice, comfortable planet. And as a little bit of a bonus, the moon's at just the right distance to give us the spectacle of a total solar eclipse every now and again. And thanks to evolution, we are able to explore and discover and understand the universe in which we live. And we can do that by building spacecraft and sending them out to explore our nearest neighbours. And we can build telescopes, which we can use to look out into the universe, and we see billions and trillions of galaxies at distances of billions of light years. We could not have done this a long time ago. Generations of stars were needed to make the heavy elements. We needed stars to convert hydrogen into helium, helium into carbon and nitrogen and oxygen and phosphorus and calcium and iron and all of the other elements that make us, us. And as we've seen in the future, in the long-term future, the universe will be dark and the universe will be boring. So you could argue the best time to exist is now. Thank you for listening.